You mentioned that, or the 1,000 CFS, threshold for the DO issue in Stockton, right? In your presentation?
Yes.
Yeah. I noted in the Bay Delta plan, there is a 1,000 CFS number, but it's only for the month of October. So were you suggesting
I'm
that
talking only about, see, I was the PI for the CalFed project for the low DO study. It's about a $2.5 million effort. During that study, we found that if the flows were 1,500 or more through the deep water ship channel, that we did not have water quality objective violations. Now that Stockton is controlling their ammonia discharges, that number can now be reduced to about 1,000, maybe even 800, but something less than the 15 for sure.
Yeah, well, I was just noting that that number's in the Bay Delta plan,
Yeah,
but
it's
it's only for
not related
October.
at all. This is flow that has to go through the deep water channel from the point of Stockton down past Turner Cut.
Oh, okay, yeah, it's a little more specific. It's it's close though. But anyway, that would be a minor modification for what I see. All right, thank you.
All right, we'll pick back up with John Rosenfield.
Good afternoon. I'm John Rosenfield, a conservation biologist with the Bay Institute, and I'll be presenting testimony prepared for the Bay Institute, American Rivers, NRDC, and the Pacific Coast Federation of Fishermen's Associations. I'm sort of glad to follow on the DWR presentation because they emphasized uncertainty, and certainly other presenters this morning emphasized how much uncertainty there is in the system. And there is. I don't want to minimize that. But I do want to say that there are a few things that are quite certain, especially from a fish or estuarine perspective. One thing that's certain for the fish of this ecosystem is that we're in the middle of a persistent, severe human-caused drought. Perhaps the fish don't know that it's human-caused, but it's certainly a severe drought. This graphic here has two panels, unimpaired flow through time and actual delta outflow through time. The bars represent the flow, which is listed on the y-axis, and the different colors of the bar represent water year types. So I want to specify that I'm not using DWR's water year types here. I'm using just 20% bins of flow so that the blue bars are wet years. They're the 20% wettest years. The green bars are above normal. That's the next 20%. Critically dry years are the driest 20%, and I've thrown in another category that's a piece of critical dry, which is supercritical years. Those are the 2.5% driest years, 97.5% exceedance. And so what this graphic shows is the water year types for unimpaired flow over time, the natural hydrology of the system, and then what the fish in the delta outflow zone see as outflow, the actual outflow. And it's complicated. You can see there's a lot less blue here and a lot more black. So I've done it's late in the day, I've done the math. Since 1967, there have been 11 wet years in the unimpaired world. The estuary has seen 4 wet years. In other words, what actually made it out of the delta looked like a wet year only 4 times. The supercritical years occurred once. 1977 was a blowout drought, right? It happens about 2.5% of the time. But the estuary has seen supercritical dry conditions in the winter and spring for 17 years since 1967. That's more than a third of years. Another way of looking at this data is an update of graphics that we presented to the 2010 flow criteria hearings. Here we see the 8 river index on the x-axis. That's a measure of available flow, measure of natural hydrology for each year. And then on the y-axis, the percent of unimpaired flow that actually makes it out of the delta. And we've broken the data series into 3 time periods. 1930 through 1955 is in the blue. 1956 through 1987 are green dots and years and line. and then the more recent period, 1988 through 2011. And so what you can see from this is a few things. At any given flow available in the ecosystem, less makes it out of the delta now than did in previous historical periods, by a lot. You can also see that currently, in the more recent years, we get withdrawals of more than 60% of the water, or 40% appearing as actual outflow, quite frequently. Finally, each of these lines is sloped. And what that means is that as conditions get wetter, to the right on the axis, more of the unimpaired flow makes it out of the delta. That's not a surprise because so much of the flow can be uncontrolled in wet years. But in dry years, as it gets drier, a greater percentage of water is removed from the ecosystem on a percentage basis. In other words, the fish see proportionately less flow in drier years. And of course, it's drier years when the fish are suffering from dry conditions. So the key points I want to make today are that there are numerous delta-dependent species that are in long-term decline. Delta outflows are the master variable, all due respect to fellow Lobo Cliff Dom. They're the master variable driving abundance for numerous delta species and ecosystem processes. I heard Cliff say earlier that some people would call this the master variable. It's something less than that. But then he went on to list all of the different mechanisms that are related to delta flow. And of course, that's what I mean by a master variable, not that it's the force in an Obi-Wan Kenobi sense, but that its flow is connected to and drives so many other variables. It's a master variable. Another point is that non-flow stressors must be addressed. No one is saying that habitat or water pollution issues should not be addressed, but they cannot substitute for restoration of flow. Increasing water diversions are the source of the reduced delta outflows. I've read some of the submissions that you've received, and they seem to imply that something else is driving the decline in delta outflows, but it's clearly increased water diversions, both upstream and in the delta. The board's focus on tracking unimpaired flows through an unimpaired flow approach, percentage of unimpaired flow approach, is scientifically sound and it's ecologically appropriate. And finally, the board should employ adaptive management to adjust flow requirements as needed. But adaptive management is not, oh, we'll deal with this problem later, or this is too difficult, we'll just adaptive manage. It requires a lot of advanced planning and advanced work. And three things that will be required to adaptively manage successfully are identification of biological and physical outcome targets that are specific, measurable, achievable, relevant, and time-bound, or SMART. You'll need to develop decision pathways to implement adaptive management. And the adaptive ranges that your varying flow and other variables between have to include the flows that you believe are necessary to support public trust resources. I mean, the flows that are necessary, the minimum flows necessary, can't be the ceiling of your adaptive management spectrum. So, as we know, numerous delta species are in long-term decline. We hear a lot about the endangered species. There are 6 of them, either federally or state listed or both. But there are also Non-Endangered Species Act species that are declining too, from salmon, bass, down to invertebrate prey species. I wanted to visualize some of these declines. I know you've seen some of graphs similar to this before, but to emphasize the point of how massive these declines are. Here's longfin smelt data from 1967 to 2011. I've log transformed the y-axis, meaning that each line here is 10 times the line below it. Okay, so we're talking about orders of magnitude. And over the time period since sampling began in 1967, we've seen a decline that's on the order of 99%, sometimes a lot more than 99%. That's a big decline in a short time. Delta smelt, similarly, 90% decline, more or less. Again, all these graphs are going to have a bump up in the last year or two. If you believe, as I do, that freshwater flow has something to do with abundances, this is not a surprise, because 2010 and 2011 were wetter than the years preceded it. If you don't believe that flows affect fish populations, then you have some other explanation for this. Winter run Chinook salmon, tremendous decline for this species, from above 45,000 to less than 1,000 in some of the more recent years. Age 0 striped bass, again, a 99% decline. Bay shrimp, not as dramatic, only maybe a 30 or 40% decline over time, but that's still pretty dramatic when it represents the base of your food web. So what do these species have in common? The answer is not that much. Some of these species have spines, and some of the species do not have spines. Some are native, some are non-native, some live a few months to a year, some live for decades, resident, migratory, the whole mix. Some spawn in the river, some spawn in the ocean. What they have in common is that they live in and migrate through the delta, and that their abundances are correlated in some fashion with delta inflow, throughflow, or outflow. Some of these correlations you've seen before, but again, I wanted to visualize them to emphasize that we heard earlier in the day, and you hear all the time, correlation is not causation, and that is true. But a statistically significant correlation, by definition, does not happen by accident. And to have multiple statistically significant correlations over decades and decades for species that really have very little in common in terms of their life history and ecology is very suggestive of a very strong driving force. So here we have the logarithm of flow, again, orders of magnitude, so that flows here are 10 times the flow here. Flows at the far end are 100 times the flows at the left end of the spectrum. And we're looking at the abundance of bay shrimp, again on a log scale, and you see the classic statistically significant relationship from 1980 to 2010 between abundance of bay shrimp and delta outflow in the spring. Here's a similar graph for starry flounder. Again, the axes are the same. You see a step change that other people have referred to between an earlier period, 1980 through 1987 in the blue, and 1988 through the recent period, or through last year in the red. This change, the vertical change, is not explained by flow, but the change over orders of magnitude in flow and abundance is explained by flow, and a significant percentage of it is explained by flow. Again, here's an example of a flow abundance relationship, longfin smelt versus delta outflow, with this step change, but still in the red line, and statistically significant order of magnitude, persistent relationship since the introduction of the clam in 1988. The point here is that for while you get fewer longfin smelt at any given flow, for every increment of flow, you get the same proportional increase in longfin smelt now as you did then. So at any given flow, less longfin smelt. For any increase in flow or decrease in flow, because these slopes of the line are the same, statistically the same, the change in abundance relative to a change in flow is proportionately the same. And this down here is a listing of several papers that have re-emphasized that this more recent flow abundance relationship is statistically significant and for real. With delta smelt and the fall habitat, things become a little more complicated, a slightly different situation, and a very different fish. You've seen these graphs before, so I'll just walk you through it briefly. Over time, an index of habitat for delta smelt has declined. That index of habitat is related to flow. So low flows here on the right, high flows on the left, and high habitat with high flow. And as the habitat index has changed, the abundance index for delta smelt has changed as well. The change is not exactly linear, and it's a little bit more of an intricate pattern. This is ecology, it's not engineering, but basically what you see is that as the habitat index increases, the low abundances that you would see have increased. You don't get such low abundances, and high abundances become more likely and even possible. You don't get those high abundances at low habitat indices. So this is the historical correlation, which is compelling. And as we've heard, last year we had the opportunity to do some targeted research because it was so wet that we were able to have a somewhat fall X2 kind of experiment. Preliminary results, and I stress that they're preliminary, it's 1 year of data, but they are suggestive of that the lower fall X2 may increase delta smelt abundance and growth rates, may reduce clam grazing, may increase phytoplankton blooms. It's 1 year of data, but it's based on this historical correlation. But it's 1 year of data. So here I want to take a stop for a second and move a little forward to adaptive management. You've been asking about timeframes. This experiment only happens in above normal and wet years. Above normal and wet years don't happen every year. And we're not, I don't think, going to be allowed to do the experiment where we have really low flows in the spring and really high flows in the fall, right? Not in an experimental way at least, right? That would make people upset. So adaptive management is definitely something we want to see happen, but there are certain things that are not really amenable to adaptive management on any kind of time frame where you're going to learn, get an answer, and go and implement it. Okay, so absolute certainty that you might get from adaptive management is not a luxury that we can take with species that are about to go extinct. We've also heard a lot of talk about, and I'm sure we'll hear more about, the uncertainty around mechanisms linking freshwater flow to viability. And I would say the use and abuse of this argument about mechanisms. No one that I know of has argued that the movement of water molecules downhill creates fish. The movement of water molecules downhill drives other forces that I believe create fish, right? The movement of water, the volume of flow, the X2, these are indicators of other processes in the delta that are related to fish abundance. So that's not to say that we shouldn't be interested in the mechanisms and we shouldn't try and narrow them down. Knowing the mechanisms can be very valuable in fine-tuning and designing our adaptive management program and our flow standards. But questions that I think the board should ask when reading about mechanisms is the mechanism that's being proposed, the hypothetical mechanism for a given species decline, consistent with the observed patterns in the delta? Is it consistent with the fact that there have been long and short-term multi-species declines? And is it consistent with the fact that there is, causal or not, this correlation between flow and abundance? And reading some of the submissions, I found that, you know, you wave your hands, you do a shell game, and look, it's this mechanism, and therefore the fish aren't declining, but they are declining. So when you find a mechanism that doesn't match up with the observable data, it's the mechanism that has to be called into question, not the patterns that we observe through our sampling programs. A second question is, can we manage public trust resources better by divorcing the mechanism, the proposed non-flow mechanism, from its connection to freshwater flow? Can the mechanism be manipulated independent of flow? Some can, many cannot, of those potential mechanisms. How certain are we that a non-flow mechanism will work? Again, certainty is not required. We have to go forward in the face of uncertainty. But before we do a major 10, 20, 30-year project, we might want to have some certainty that it's going to work if we're not going to take the intermediate action of increasing flow. And again, this gets to the point of how long will it take to find out whether the non-flow alternative worked or not. The board in its 2010 report wisely realized that flow and physical habitat, one of the potential other stressors, they interact. Flow interacts, as Ted Summer said in the panel before, flow interacts with most of the mechanisms that we talk about as being potential drivers. But because they interact does not mean that they are interchangeable. We still have to address the flow issues. Okay, so the next point was that increasing water diversions are the source of reduced delta outflows, and that they cause this perpetual drought that I talked about in the beginning. This is a graphic that I believe we've seen, or we will see, showing increased water diversions from 1956 through 2011 from the Central Valley Project and the State Water Project. This is a fairly continuous increase in exports, right? There are a few droughts in here, but basically we've been continuing to increase water exports since these projects came online, and now most of the increase in water exports is due to state water project operations. And in 2011, even though it was not by far the wettest year on record, it was the year that we exported the most water on record. So we are exporting a lot of water from the Delta, and that obviously impacts the Delta outflow. This is not solely a problem caused by the State Water Project and Central Valley Project. This graphic shows flows into the Delta from upstream. So obviously what doesn't flow into the Delta can't flow out of the Delta. And I've averaged here by decades the mean actual inflow to the Delta divided by the unimpaired flow. What percentage of flow in the Sacramento or in the Delta drainage actually makes it to Delta inflow, and that has declined pretty steadily over time as well. The dotted line shows the maximum, within a decade, the maximum unimpaired flow percentage that reaches the Delta, and the red line shows the minimum. And clearly, the minimum has gotten to about 50% or lower. But it's not, as was said before, it's not just the timing, it's not just the magnitude of flows that are of concern. The fish species and ecosystem processes in this area, in the Delta, are sensitive to the timing, duration, and frequency of critical flows, and they're as important as the magnitude. Here we see for 2010 the unimpaired hydrograph of Delta inflow. And in the red, we see the actual hydrograph, what actually appeared as inflow to the Delta. Obviously, the red line is lower than the blue line. Less water makes it to the Delta than would if there weren't diversions. That's pretty obvious. But we also see that this results in a sort of a flatlining. While there are various pulses of flow here that fish species may use to cue migrations or reproduction, there are far fewer and less dramatic pulses in the actual outflow curve. And this, by the way, is a problem that an unimpaired flow approach would begin to address by making the red line more closely track the pattern, the shape of the blue line. But I wanted to show how the setting of the magnitude in an unimpaired flow approach also affects timing, duration, and frequency of these critical flows. If we took a hypothetical flow criteria, this black line here, it's just a hypothetical. I'm not suggesting that this is some minimum flow necessary for something, but as a hypothetical, this flow produces some benefit to fish and the ecosystem and the public trust. At the bottom, I've graphed out the duration, and by implication the timing and frequency of when we would attain this critical flow level under the actual, which is in these blobs in red, and under the unimpaired, which is the markers in blue. And what you see is that for this hypothetical flow, it occurs more frequently in the unimpaired than it does in the actual. It occurs for longer periods, and it occurs at different times of year than we see in the actual flow curve. That may be preserving important functions for different fish species, and so that's something to consider as you set a standard for unimpaired flow. Is it's not only the magnitude of flow, but how it affects the frequency, duration, and timing of critical flows. The best available science really supports this flow standard as you've structured it in the flow criteria report as a percentage of unimpaired flow with narrow time window for the averaging window so that the actual flow tracks the unimpaired flow. The National Research Council said pretty clearly that if the goal is to sustain an ecosystem that resembles the one that appeared to be functional up to the 1986 through 93 drought, exports of all types will necessarily need to be limited in dry years to some fraction of unimpaired flows that remains to be determined. Setting this level, as well as flow constraints for wetter years, is best done by the State Board, which is charged with protecting both water rights holders and the public trust. In addition, a paper by Richter et al., a noted independent NGO scientist and some academic scientists, did a study of different flow standards around the world, both their structure and their kind of magnitude, and found that a large body of scientific literature supports the natural flow paradigm as an important ecological objective to guide river management. the percentage of flow approach has several strong advantages over other approaches. And I'll let you read the quote later on. Obviously, we're going to need to do adaptive management in the system because there are a lot of competing forces and there is a lot of uncertainty. Flow standards are potentially well suited to adaptive management. Freshwater flow standards have a potentially high magnitude effect and high certainty of positive effect. So there's something you want to implement rather rapidly, and they can be implemented and they can be revised rapidly, unlike some other actions we might take. Changes in those flow standards don't involve abandoning sunk costs, like constructing a new facility or to treat wastewater. Or I'm not suggesting that any other actions shouldn't be taken. I'm just saying that flows have the unique advantage of you can change them next year if that's what's needed. And the costs and impacts can be distributed somewhat equitably among contributors to flows. But like I said in the beginning, adaptive management is not just some way that we make this all a lot easier. It actually makes things harder. The 2010 flow criteria may not be sufficient to attain desired outcomes in this ecosystem, or they may be more than enough. That's why we would have to study and adapt. I want to point out that 75% of unimpaired flow, as the board has suggested might be necessary for Delta outflow and Sacramento River inflow, is low compared to standards of river protection elsewhere. Again, citing the Richter et al. 2011 paper, and obviously these are different rivers in different parts of the world, but they have all of these rivers have been highly modified, so it's not like these are pristine rivers. And they found that the typical range of protective standards resulted in a range of allowable cumulative depletion of 6 to 20% of normal flows. A moderate level of protection is provided when flows are altered by 11 to 20%, and alterations greater than 20% will likely result in moderate to major changes in natural structure and ecosystem functions. Okay, so 75% is a wonderful place to start, and we will need to adapt, but we shouldn't expect that adapting just means going lower. It may involve going higher as well. As I said in the beginning, adaptive management requires development of some tools. It's going to need a logical and transparent planning framework. In our submission, we've described and will continue to describe in subsequent submissions a process we call the logic chain. This is a planning architecture that forces one to articulate desired outcomes, key assumptions, and the uncertainties that you hope to narrow through adaptive management. It also specifies that actions, adaptations, and efforts to reduce uncertainty are going to be in service to achieving predetermined outcomes, which we call goals. And those goals are defined by SMART targets, specific, measurable, time-bound, et cetera. And this goes both for the water supply end of things and the ecosystem end of things. In order to adaptively manage, you have to know what you're managing towards, both in terms of water supply and ecosystem outcomes. There will have to be clear decision pathways with management triggers. When will progress be evaluated? What circumstances call for a change? These are questions that should be worked out in advance, not on the fly. I don't think we need to change anything. You know, it's not that bad. That's management reactivity, not adaptive management. And again, adaptive ranges that do not, we need adaptive ranges that don't fall short of minimum flow criteria needed to attain the ecological goals and SMART targets, because if you don't set the flow criteria to meet the target, then it's easy to say that, oh, you increased flows and it didn't work. It can only work if you use a range that encompasses what you think will be necessary to meet your targets. And with that, I'll pass it on.
Okay, who's next?
I'm John Kane. There we go. Hi, I'm John Kane with American Rivers, and I'm going to keep my comments brief today and defer my presentations to workshop number 2 and number 3. But I wanted to say, first of all, I hope you will really pay a lot of attention to this logic chain approach. I believe John plans to present more on that later. I will present on that during workshop number 3. It's very related to how you might use models. We've put a lot of time into that collectively through our organizations, and it's been reviewed by at least 3 scientific panels. So it is not something we just made up, but something that has gotten a lot of thought over a long period of time. Secondly, I just wanted to quickly touch on this idea of flow as a master variable. And if you think about it, if you have high outflow, it means that you have high flow conditions for hundreds of miles of rivers in the Central Valley and inundation of side channel habitats and floodplain habitats. You have a huge footprint change in the system. So you trigger all of these different processes, and there's very strong evidence that inundation of floodplain habitat is very good for Chinook salmon, Sacramento splittail, and other species and ecosystem processes. One new development that I'd like to tell you more about in workshop number 2 is the Central Valley Flood Management Plan that was just approved by the Central Valley Flood Protection Board, and it calls for expanding floodplains and floodways in the Central Valley to accommodate flood flows, and can have huge potential benefits in terms of restoring floodplain habitats for fish and birds. But it's really only going to work for fish if these floodplains are inundated frequently. And if you have high outflow, you are pretty much guaranteed that any kind of floodplain that would get inundated by those flows would become inundated. Without this master variable, you wouldn't have that footprint of aquatic ecology. So when you start to think about what it means to have high outflow at the bottom end of a huge watershed, you realize that you're not just talking about changing the low salinity zone in a certain area, you're talking about changing how everything is working in the entire watershed. Thank you.
Good afternoon. I'm Tim Stroshane. I'm a senior research associate with the California Water Impact Network. It's on. Oh, yeah, it's on. Yeah. How's that? There we go. Okay. Our testimony has 2 sections. The first section deals with the South Delta salinity issues, the Central Valley project, and the project's difficulties complying with interior South Delta salinity objectives. The second section describes the Selenium Reservoir in the San Joaquin Valley and Selenium's behavior in different aquatic environments. I conclude the presentation with some recommendations for the Bay Delta plan, but I first want to say that salinity reduction is needed to prevent harm to the South Delta agricultural beneficial uses and to their water right holders. Selenium reduction and sequestration is needed to prevent contamination and ecological damage to South Delta fish and wildlife beneficial uses, as well as human public health. Through Seawind's presentation, we intend to show from recent salinity and selenium research that greater freshwater flows to and through the Delta, the South Delta, are necessary to achieve both of these purposes. The State Board established in D1641 that the Central Valley Project mobilizes a large source of salts from the San Joaquin Valley that enter the San Joaquin River system. And the activities of the Central Valley Project greatly reduces the assimilative capacity of the San Joaquin River as well. In D1641, the State Board also made the Bureau responsible for significant deterioration of water quality in the South Delta. This slide shows decadal trends in total dissolved solids at Vernalis. Within 4 decades, salinity nearly doubled at Vernalis from an average of 228 milligrams per liter total dissolved solids to 427 milligrams per liter in the 1960s. These changes were largely due to the Central Valley Project. Under D1641, the State Water Board, the State Water Board made the Bureau and the Department of Water Resources responsible for complying with the interior South Delta salinity objectives. Along with the long-standing salinity objective at Vernalis, the board designated 3 compliance monitoring sites in the South Delta listed in this slide. Exceedances began almost immediately when the compliance period began in 2005. And they have recurred in most years since, especially at the Old River Tracy Boulevard site, shown as the orange curve in this chart. Exceedances recur and worsen in magnitude and duration, as shown by the yellow regions of this chart. Neither the new responsibility nor the salinity objectives seemed to work out that well for the board, DWR, and the Bureau. Because of these recurring exceedances, the State Board placed the Bureau and the Department under a cease and desist order, beginning in 2006. Compliance remained elusive, and the Board relaxed the CDO compliance deadline from 2009 to 2014. In agreeing to the delay, the Board required the Department and the Bureau to perform 2 modeling studies. The first of these, wow, that's odd. The first of these was DWR's low head pumping study in 2011. The idea behind low head pumping was to shunt higher quality Sacramento River water in the South Delta upstream of temporary barriers in the vicinity of the interior monitoring sites. DWR's exhaustive modeling effort found that low head pumping would not be effective at reducing, let alone obviating, the threat of noncompliance at the interior South Delta monitoring sites. DWR's study also found that depending on the monitoring site, 83 to 93% of all salty water reaching the South Delta originates with the San Joaquin River. This finding strongly suggests that the State Board, DWR, and the Bureau should be looking upstream for solutions to the salinity problems of the South Delta, because existing saline San Joaquin River flows overwhelm Old River water quality. The second study was the Bureau's 2011 dilution flow study. In essence, the dilution flow study asked what flows at Vernalis would be needed to meet surrogate objectives at Vernalis that would lead downstream to interior South Delta salinity compliance, and what would be the water cost. The Bureau found that during winter and in wet years, the water cost of dilution flows could be perhaps as low as 100,000 to 200,000 acre-feet. During summertime and the driest of years, the water cost could rise as high as 1.4 million acre-feet, coming from some unnamed east side reservoir, according to the study. The Bureau's dilution flow assumes no change to the salty irrigation imports via the Delta Mendota Canal. This made it easy for the Bureau to conclude in the dilution flow study that to achieve full compliance would likely require an unreasonable amount of water. Seawin respectfully wishes to remind the Board that it is not up to the Bureau to determine what is an unreasonable amount of water. That's, of course, your job. Meanwhile, salinity exceedances continue in 2012, and they continue to pile up where Old River passes the Tracy Boulevard Bridge. The State Water Board has shown its intention to keep Vernalis salinity objectives as they now are, but proposes to relax the interior South Delta salinity objectives. Along the lines of the Bureau's dilution flow study design, the Vernalis salinity objectives would become like the surrogate objectives in that study for helping the Bureau comply with interior South Delta salinity objectives. Seawin sees this as a prime example of moving the goalposts to help an ineffectual home team score. CWIN urges that the board incorporate into the Bay Delta Plan analyses of, first, the vicious cycle of recirculation, reduced assimilative capacity, and exports of high-quality water from the resulting from Central Valley Project operations. Second, we recommend that the board should include the recent Bureau and DWR modeling results and their implications for interior South Delta water quality and salinity regulation. Third, the board should analyze the effects of the board's interior South Delta salinity proposal in light of the Clean Water Act's anti-degradation policy and in light of the potential to injure South Delta beneficial uses and their water rights. Finally, we also recommend the plan's implementation program should include investment in further research into the salinity problems of the old river monitoring sites. Okay, I'd like to switch gears now and cover the second portion of our testimony, which deals with selenium science and modeling material. This map shows the major areas of highest selenium soil concentrations in the western and southern San Joaquin Valley. They represent in map form the locations of California's largest selenium reservoir. Since the 1960s, California and the federal government have employed several management approaches for handling the selenium reservoir. There yet remains nowhere to put the saline and saliniferous waste from irrigation use that does not somehow redistribute the effects of the selenium contamination problem. The State Water Board, however, seems to prefer the master drain as a long-term solution for selenium management. D 1641 contained language stating that a valley-wide drain exporting salts and selenium would be the only feasible long-term solution to San Joaquin Valley drainage problems. Recent selenium toxicology and ecological risk literature characterizes the selenium reservoir in some new ways that I wanted to describe for you. It's essentially an unlimited total load in the San Joaquin region's source rocks and soils. Consequently, the rate at which the reservoir can be drawn down and its toxic threat removed depends on one's management assumptions of the selenium. The threat of selenium loading, contamination, and ecological risk under the board's unofficially preferred master drain system, according to Presser and Luoma, would still take 63 to 180 years to eliminate selenium from just the western San Joaquin Valley. The societal timeframe for slower methods of selenium abatement would take far longer. Now I wish to focus, Now I wish to focus your attention on how selenium moves through different ecosystems. Current selenium regulation is done by setting criteria for selenium in the water column. Recent research, however, provides strong evidence that such existing criteria are not protective enough. The current approach does not address the accumulation of selenium and its toxicity in the tissues of predators, including their reproductive systems. The pathways to predator tissues vary with hydrological and ecological differences across aquatic environments. Flow energetics and food webs vary. Selenium regulation needs to take account of this variability. I'll make sure I change the slide this time. Presser and Luoma identify and quantify factors affecting selenium entry into food webs through an ecosystem scale modeling approach. They compile empirically determined partitioning factors shown in this table on this slide as K sub D, quantifying selenium's tendency to dissolve or undergo phase transformation and deposition to sediment, and hence become bioavailable. High values of K sub D, as shown in this table up here, occur with low energy environments like estuaries and reservoirs. It's much easier for selenium to leave solution in those environments and ultimately become bioavailable. Presser and Luoma also quantify food web factors that indicate relative tendencies for selenium to bioaccumulate in consuming organisms such as clams and insects, and as prey consumed by predators. They relate these factors ultimately to critical tissue concentrations and to toxicity in the tissues of the predators. By quantifying the movement of selenium from water column through prey species to predators, they demonstrate that selenium behavior entering food webs first depends on the energetics of the aquatic flow regime into which selenium enters. I recalled as I was preparing Seawin's testimony that I had seen a presentation by a biologist with the Geological Survey named Amy Kleckner back in 2009. Her presentation was on selenium uptake in what was known at that time as corbula. You've heard it today mentioned as potamocorbula. And anyway, it's this invasive clam. At the 2009 Bay Delta Science Conference, and I decided I would try to line up her corbula data with Dayflow X2 data just to see what would happen. Her data eventually were published in 2010 by the survey. This is the comparison chart that I developed. The blue curve is the X2 isohaline. It is measured in kilometers from the Golden Gate. And the red curve reflects selenium concentrations in corbula specimens gathered at Chips Island by Kleckner and her team between 2002 and early 2010. When X2 rises in this chart, selenium tissue concentrations in sampled corbula specimens also rise. When X2 decreases, that is, moves west with high flow volumes, selenium tissue concentrations in corbula specimens fall at Chips Island. I don't know the source of the selenium that these corbula clams are eating, but I feel that remains for others to study and hopefully determine. Possible sources, though, may include the North San Francisco Bay oil refineries, as well as potential selenium loads coming down the San Joaquin River through the Delta estuary. Based on the results of these selenium and salinity studies, SWRCB recommends for the Bay Delta plan that first, the state board should lower the water column selenium objective. And we've included on the slide that we recommend that after the findings of Presser and Luoma, that they be reduced from 2 parts per billion to 0.2 parts per billion. Second, we urge you to keep the water moving through the delta somehow. The state board action steps that lengthen residence time and reduce through flows in the delta should be understood in this context. Whatever the source of the selenium for the Chips Island corbula clams, the X2 selenium uptake comparison should give the state board some pause. The board is likely to make decisions, for example, about the proposed peripheral tunnel project and its water rights, as well as CVP and state water project water right permit time extension requests. And the board, as I've mentioned, has also expressed at least tacit support for a San Luis drain, possibly discharging saline and saliniferous effluent to the Bay Delta estuary. Each of these actions alone could either greatly lengthen residence time of waters in the delta or increase selenium bioavailability. Taken together, they definitely would do both. Finally, we think at SWRCB that it is better to stop pouring imported water on the problem of selenium movement by adopting a strategy in this plan for more western San Joaquin Valley land retirement in order to sequester selenium in the valley and prevent it from getting mobilized to contaminate the Bay Delta estuary and the lower San Joaquin River. And that concludes my remarks.
Okay, Tom.
I'm going to talk about the low salinity zone and how it's been affected by the flow and export standards, particularly in May, June, and July when the fish are most susceptible to changes in the low salinity zone. I'm going to focus on what's new, 2011, 2012, so don't bore everybody with all the other years. These are 2 new years in the sequence of 34 years that I've examined, and I've treated each year as a new adaptive management experiment. And there's 17 years under 1485 and 17 years under 1641. And every year is different, and every year teaches a different lesson, but there are a lot of common lessons, and I'll try to go through a few of them here. I don't need to talk about why it's important, but basically what happens in May, June, and July, the question is whether the low salinity zone gets into the vise. And the vise is where the smelt and their low salinity zone habitat get pulled from the delta by the exports, and they're pushed to this point by incoming reservoir water and incoming salt water. And I've seen this happen in maybe half the years. It doesn't happen in a year like 2011 because there's too much water in the smelter downstream, but I'll give you some examples. But this vise has occurred every year since about 1978, which was a wet year, but it did occur. I'm just going to focus on 2012. In March 2012 this year, the low salinity zone, which is the green dots, these are taken from the 20 millimeter survey that people talked about earlier. It shows you where the low salinity zone is in the green area. And it's down in Suisun Bay, and they're nowhere near the vise. The low salinity zone is down in Suisun Bay, and the outflows are pretty high. And the longfin smelt are on the left. They're down in Suisun Bay with the low salinity zone, and the delta smelt on the right are still up at the front of it, sort of at X2 and above. And then in May, we had the nice vamp in the first part of May, and low salinity zone is still down in Suisun Bay. Outflows are high, exports are low. Late May, I'm showing red as greater than 2,000 EC, which is really sort of like the X2 point. So it's not really the full low salinity zone, but the green is sort of everything above X2 up to about 500 EC. And these are mostly surface EC, so the X2 is really bottom 2,000 parts per thousand salinity. So they're a little different, but I tried to make them close by showing the red line at about X2. So you can see in late May, after vamp, exports are coming up. Outflows been falling during the month of May from 28,000 to 6,000. And 6,000, if you remember from the past presentations, we'll put the X2 up around 85, which is pretty far up. So it's starting to head up towards 85. Right now, at the end of May here, it's still way down by Chips Island, but it's starting to move up. The first week of June, it's moved up. 6,000 outflow, And this is the vice. This is what I was talking about. When the low salinity zone, the green, gets up here in the western delta, you get the fresh water pushing in and the salt water pushing in, and the exports are going to start taking from the green zone, I call it, the low salinity zone, and the smelt. And you can't see it very well there, but those little yellow marks around some of these dots, this is where the smelt are. They're in the low salinity zone. In late June, things relaxed a little bit. I don't know if somebody got scared and raised the outflow a little bit, but that's exactly what happened. I'll show you it in a minute. It kind of backed off, but the vice is still operating in late June. And this brought me to be very concerned when it happened about the delta smelt, because we had so many last fall, and then we had the good spring index and the 20 millimeter index. So I was pretty worried about the summer tone-net index at this point, knowing that everything comes about a month later than the actual sampling, because you have to wait for the processing of the samples. And here in early June, we were just looking at it, and you see the longfin on the left are way down in Suisun Bay, even though the low salinity zone has moved upstream. And the smelt on the right over here are still concentrated in the low salinity zone. So I quit worrying about longfin smelt by this point because they're downstream, but they are susceptible to the bad clam water. And that's probably what happens to them. First week in July, or second week in July, the vice is really strong in the delta. There's high inflows, and the X2 and the low salinity zone is very susceptible to exports. And I'll show you in a minute what's going on. Oh, right here. This is the whole period of June and July this year. You can see in June we had the green is exports. We had low exports, but we had this 6,000 outflow, which meant the X2 is going to come up to 85. And we had inflows down around 12, but they were rising. And then here's the relaxation period. I don't know if somebody was trying to protect things, but something was going on in here. The standard for a dry year like this is about 6,000 outflow, so we're following the standards. But then the standard changes on July 1st. This is the EI standard. This is the real problem. I think it caused the pod in 2001 and 2002. The EI standard starts on July 1st, and boy, do they start on July 1st. You can see exports went up to 11,000 on July 1st. Outflow dropped. That means they're taking the water by pulling the low salinity zone upstream. And at the same time, they're pumping in or releasing more water from the reservoirs to try to make up for it. And so what you have is more reservoir water coming in to make up for the high exports, and you have the red salinity X2 moving upstream. So that's the vice, and the EI standard and the low outflow standard for June in a dry year are really the problem for the delta smelt. And at this point, I didn't know what the delta smelt were doing. I just found out today that the index for the summer tone-net, which was determined in 2 surveys in the middle of June, was probably one of the lowest on record, despite last fall and this spring's 20 millimeter. And so I would blame most of it on this 6,000 outflow. So the problem in 2012 was this low 6,000 outflow, and the first part of June and late May. And if you want to do an adaptive management experiment, we should have had more outflow. Even though the standard says 6,000, we should have had more outflow because we knew this was going to happen. And any delta smelt biologist would know this was going to be a disaster, especially after you had a new recovery last fall and this spring. So that's where adaptive management can come in. Going way backwards. In 2011, it wasn't a concern because the low salinity zone in all through July and August was down in Suisun Bay, and the vise was not operating. It was completely safe. The smelt were down there, and we could export 11,500 every day, and nobody would care. And the smelt wouldn't matter. There probably are some impacts, but at the end of September, we had the highest smelt index in 12 years, essentially, after July, August, September of 2011. It wasn't necessarily the 75X2 in September and October that people talked about earlier. It was all of this. It was the low X2 in June and July and August too. And you can see the outflow, which is the red, orange, and the inflow, which is yellow, and the exports were maxed out 11,000 all through July, and from the middle of June through July. There's just a lot of water in the system, and X2 is way down in Suisun Bay, and the exports of 11,000 and minus OMR flows are just not a problem for the smelt. And here's the first year of the pod, or what I call the first year of starting the pod. 01, 02 is pretty much the start of it. We've had 95, 96, 97, 98, 99, 2000 under 1641 with the EI standard. All those are wet years, so nothing happened. The standard hardly applied. But 01 and 02, I looked at it when it happened when I was working with CalFed. I knew the EI standard was going to be a really big problem in years like this. And it absolutely was. You had the vise operating at maximum conditions in June because of the low outflow standards for June. And the smelt in June, or these are the same two periods, the smelt are just sitting right there in the low salinity zone at maximum risk to exports and the vise. And the reason all the smelt are in the lower San Joaquin channel is because they've all been taken out of the other channels. They're gone. And you can see in 01 here that the magic EI standard came on July 1st, and you can see what happened. At least it was kind of smooth. It wasn't an abrupt shock. But your exports went up to 8,000, 9,000, and it wasn't too bad. And really the pod crash really didn't happen this time because I think this was kind of easy on them, and they only went down a slight margin in the fall index in 2001 from the previous year. So I think it was kind of easy on them, although you can see that the west, which is similar to OMR, it's the San Joaquin negative flow, got pretty bad in July. And you can also see that the outflow was pretty high in June. It was up around 8,000 most of the time. So it was a pretty easy year for them, even though it was the first year of the pod. Oops, backwards. 2002, we've got a real vise operating. The July 1st again, the EI export limitation comes into play, and outflows dropped sharply, but they added some inflows. And again, adding inflows is part of the problem. The blue water that they're adding to make up for the exports and to allow the outflow standard, the blue water is warmer, it's clearer, it's less turbid, has less nutrients. It's essentially reservoir water that's being dumped into the delta to make up for all this export demand. And the low salinity zone is becoming a mixture of the red water, which is the salt, and this new blue water. So it's really not green water. It's kind of a mixture of the two. And all the green water that was good is gone. It's been exported by this time. And the water that's going into Suisun Bay, where all the clams are, is not really green water anymore. It's mostly the blue water that was coming from the reservoir. So everybody's hurting by this. And this July 1st EI standard is the major problem, and then the June outflow standard is another part of the problem. 2009 is another dry year. Same thing happens. On July 1st, they just turn the pumps on. And, but you can see there's also the poor June outflow requirement for a dry year. It's down around 3,000. And in a lot of years that will get them first. But if that doesn't get them, the July 1st EI standard will get them, because I can remember when that standard was applied that the water contractors kind of celebrated because they knew they could turn the pumps on all the way on July 1st. And having 11,500 or so for July, August, September, when they used to have limits like 8,000 or 9,000, is a kind of a windfall. And that's why we have these record export years like 2011, even though it didn't hurt the smelt in that year. So you can have the flow standards as delta outflow, X2 location, doesn't really matter. You can export limits or export limits, and you can have QS or OMR flows, and these definitely have to apply in May, June, and July. I'm not so sure about September and October. I have never really spent a lot of time on that. I'll spend more time in the next workshop on that. Okay.
Thank you. Questions?
Questions? Felicia?
Great. Thank you, panel. Thanks for coming and hanging in there all day today. And thanks to the audience for hanging in there, too. We've had a lot of interesting information today. This kind of harkens back to the Fish and Game presentation and maybe some of the science, the invited panel. But also, Dr. Rosenfeld, you brought up this issue, which I found interesting and wanted to bring a little light to. Today, we've been speaking of the low salinity zone and mostly the effects therein and some nuances about how it gets fed by adjacent areas, subsidized, if you will, but how it is notable how low the productivity is. One of the points that Fish and Game has brought up relates to the bay part, the bay delta. We've been talking a lot about the delta today, and maybe, Doctor, you can expound on this, but you know, I'm interested in some sort of secondary effects of the low salinity zone as it relates to the bay and the species there. You know, we mentioned that starry flounder, bay shrimp. Another species is the Pacific herring, may have some of its abundance or productivity related to the low salinity zone. And then of real interest to me is this northern anchovy, you know, a dominant species in the bay, very important for the food web. And a statement buried in the written information that I got through last couple of weeks about how the northern anchovy may be impacted by reduced productivity in the low salinity zone. Can you speak to any of these mechanisms or their importance? Because we've been talking about smelt a lot today.
I'll try not to expound too much.
But
so we
also,
don't-
yeah, I want to also just point out, you know, diversity and its importance. And we've been talking a lot about specific species. The DWR put up a graph that wasn't altogether inspiring about, you know, how there weren't that many native species in the 80s, and there's not a heck of a lot now to speak of, you know, in the delta. But how about if in your comments to touch on the issue of diversity, these management decisions we're making here, how that would affect the San Francisco Bay?
Okay, I'm going to come back to that second question and ask you to clarify a little bit. But on the issue of how the low salinity zone or the estuary as a whole subsidizes things downstream into the ocean, I think it's a great point. I mean, estuaries are nursery areas for the two examples that we've talked about today, bay shrimp and starry flounder. But other fishes as well, and even beyond the fishes to things like orca whales. The nymph's biological opinion included fall run Chinook salmon in it because of their impact on this ocean-going species. So I was reading in the comments, I forget who submitted them, about, again, there's a lot of talk about what's really driving the system here. Well, the ocean influences the bay and the estuary as well, and that's true. Some of our species here don't go to the ocean, so it's not a direct connection for them. But the reverse is true as well. There's a flow of organisms, nutrients, etc., from the estuary to the ocean. So, if you want to be concerned about even more than you already have to be concerned about, then I would say that that is an area of impact and certainly a public trust value that exists beyond the low salinity zone, yet is affected by river flows, river inflow, delta outflow, etc. I'm not sure if that is that.
Well, yeah, and just
relevant?
interested in mechanisms, that just the response in biological populations, to cues that may be related to low salinity zone. Is the lack of productivity in the low salinity zone holding back the recovery of species downstream in the bay? There's a lot of investment. I'll put my 20 years of work out there as far as restoration of wetland habitat in the bay, and the work many other people have done. And, we're looking for a signal of response in terms of that investment of public, funds and efforts. So, we're not seeing necessarily, we may have seen some. I know that on a local scale we have seen some response of native species and tidal restoration.
Yep.
But so I'm bringing up the bay,
Right.
in terms of.
Well, I think you've already heard Dr. Kimmerer talk about the effect of fish leaving the low salinity zone for lack of food or differentially surviving there. We've talked about food web subsidies in terms of phytoplankton and even down to nutrients, but just think of the fish as part of the food web. Right. These are a lot of small fish, longfin smelt, delta smelt, split tail. Right. Some of those fish, not all, some go to the ocean, and some their rearing environment is the bay, and then they go to the ocean.
Right.
They are food there for something else. So yes, in general, the low salinity zone is connected to the bay, just as the rivers are connected to the low salinity zone. So I know that the board has to, in order to make sense of this, divide things up into manageable units for policy and just understanding. But in reality, these things are it's a hydrological and biotic continuum, right? These are not little discrete sandboxes where this is the low salinity zone. You have to go through a door to get to some other zone. It's sloshing back and forth, and they are feeding off each other.
On the connection with diversity.
Yeah,
on
the diversity point. I would say that the Bay Delta is, it depends on what time perspective you're looking at things, but I consider it to be an area of extreme diversity. There are 4 temporarily distinct runs of Chinook salmon in the Bay Delta and its watershed. That's more runs than any river system in the world. There are endemic species some of which we haven't talked about today, but split tail, delta smelt, etc. Distinct population segments of green sturgeon, etc. And San Francisco Bay, biogeographically, is a division point between 2 different kinds of biotic regimes, or at least historically has been its interesting biogeographical point. And so it represents the southern extremity of the ranges for a lot of these species, and therefore the temperature, rainfall extremity, and the interaction with other species extremity for a lot of these species that aren't, for instance, having the same experience in Alaska or Canada, right? Mm-hmm. So this is an area of historical diversity, and I would venture diversity formation that could be very valuable in a world that's changing faster and faster in terms of our adaptability to that change.
Yeah, good.
I think this is a question for Tim. You had in one of your slide an interesting statement that flow standards are easily implementable and revisable, or at least can be revised or can be implemented and revised in a short period of
No,
time.
that wasn't me. I think
That was somebody. Okay.
that-
Sorry. Yeah. What did you mean by that?
Right. I'm sure from your perspective that they're difficult to implement and they take a long time, and
Yes.
yeah, I don't want to not respect that. What I mean is that compared to earth moving projects and building facilities in terms of the permitting and the construction and the operation and then the time that it takes to get a response, right? Those are long-term prospects that it's very hard to walk back from, right? Once you've built a $16 billion set of tunnels, it's right, it would be hard not to use them. So I don't want to minimize the care and the time that has to be put into and the impacts that water quality standards have, but certainly in cases of severe drought or flood emergency, they can be temporarily waived, they can be permanently modified. So it's not that they're easy, it's just that in terms of a time frame of if you wanted to take action, one of the most rapid actions that could be taken would be increasing freshwater flow, right? It can certainly happen more quickly than restoring tens of thousands of acres of tidal marsh habitat, for instance, which is something that we should explore, but we don't own that land, so it takes a little time to do that. So in terms of the time frame for management, I would say that of the available knobs that have a big response and a certain response, freshwater flow is something that can be adjusted relatively quickly compared to other things.
I'm disappointed. I thought you had a secret shortcut.
Can I add to that just a little bit? So you may have two competing hypotheses. One is that it's habitat, and what we need to do is restore habitat. Or another hypothesis is that it's flow. And I think the point that John's making is this: if you're going to restore habitat, how much habitat do you need to restore to actually increase the food supply sufficiently to actually make a difference in the population? Well, it's probably tens of thousands of acres. And that's going to take a long time. I know I personally have been working on a tidal marsh restoration project that DWR is the lead agency on. They're the biggest. I think it's fair to say that they promote the habitat part of the hypothesis. It's just taken a long time to actually get these things in the ground. We're not sure when it's going to happen. A flow management action could be done relatively quickly. There is a cost on someone. And if it doesn't work, it's reversible. But the habitat restoration, tidal marsh, is not a reversible action. Once you do it and create a wetland, it's there. We hope it will have positive benefits. But the reality is we'll have to have it in place for a minimum of 5 to 10 years to really know, to watch the marsh evolve and to really know what kind of species are utilizing it and whether we're really getting the signal we expect to get out of it. So the flow actions are something that can be done quicker because they don't involve a lot of earth moving, and they're something that are reversible.
Staff, do you have a question? We do have one. Why don't you all just stay there for just a second? We have.
And my lack of question isn't a lack of interest. It was incredibly interesting, and I'm still digesting it, so thank you.
We have one person who is not going to be here tomorrow for public comment, and so Joe McGann. Yes. Okay, great. Then Thank you very much for coming today, all of you, and certainly for the panelists and for the staff and for Brock, who helped organize this. We will be reconvening tomorrow at 9 o'clock, and we'll be doing day 2, and I expect day 2 will last until approximately 5 o'clock as well, based on what I've seen today. Thank you.